I'm more of a scheduling guy than a planning guy, so if you were disappointed about the first part, maybe you'll be excited about the second part. So, scheduling is quite different in a number of ways. Both the way it's studied and in, obviously, the problems that we're studying. And so it's quite a sort of a cultural thing if you're coming from a classical AI planning perspective and what constitutes research and what constitutes where the academic community is going to kind of understand how the scheduling community is actually somewhat different. So we'll talk about scheduling. Mostly I'm going to be talking about what the problem of scheduling is. We'll also get into the style of research that schedulers tend to do. We talk about some differences with AI planning. Talk about some exact solution techniques. Okay, that is, we're finding improving optimal solutions. Okay, so CP, I'll talk about mixed integer programming, and I'll talk about decompositions, because these are some of the state-of-the-art stuff that has come out over the last few years. There's a particular hybrid technique that's based on decomposition, and so I'm going to spend some time. Most of my examples are going to be from there that are going to use mixed integer programming and CP, or sometimes CP in a decomposition technique. And there's some connections with some of the things that Rowan was talking about this morning when we talked about the multi-agent stuff. And the bulk of this is going to be talking about three different example problems. One's a generic resource allocation and scheduling problem. Another one's an aircraft maintenance problem that uses really all the same things, all the same techniques and concepts from the first one. And then hopefully I'll have time to go into this. This is a rather complicated problem that uses all sorts of queuing theory and sophisticated stuff, as well as demonstrating something different about constraint programming that I can hopefully tell you about. All right, so scheduling. It's really about the allocation of resources to activities over time. I'm going to talk about activities, tasks, blah, blah, blah. I'm going to be hand-wavy about what those things are. But, as an example, if you're in food manufacturing, you have machines that are going to be mixing the ingredients and heating them and doing whatever you want, right? So you have machines here that you're scheduling. If you're at a university in administration, you have to figure out your classroom schedules and your exam schedules. How do you allocate classrooms to lecture sections and students to those lecture sections? So you think about that scheduling. If you're FedEx, you have to figure out how to deliver all your packages. So now this looks like a logistics problem. Can be looked at as a scheduling problem, where you have to schedule the set of deliveries you have, given your multiple modes of transportation. These are mathematically hard problems. Most of the interesting ones are NP hard, industrially, and economically, and environmentally important. Right? The fundamental thing that we're going to try to do here is derive optimal schedules, and optimal depends on whatever cost function we're minimizing. In many real-world cases, in some real-world cases, we're actually interested in minimizing things like CO2 emissions. Okay, so FedEx has actually I think it was UPS, has a famous example of doing their route planning in downtown New York, and what they've actually minimized is left-hand turns. If you've ever been in downtown, in Manhattan, you might imagine why they want to minimize left-hand turns, right? Both time-wise, because they're sitting there idling, but also that was a huge amount of their CO2 emissions was sitting there idling in traffic. And so they were actually routing to minimize left-hand turns, which is a very interesting optimization criteria. So this is underlying scheduling. Optimization is underlying an awful lot of the real-world economy out there. If you came here on a plane or a train, chances are you've got, well, I would be surprised if there isn't some optimization technology going on to do the flight planning, the crew planning, food on your plane, et cetera, et cetera, et cetera. The allocation of your resources at the airport. All of this is using real optimization technology. Most of it is based on mixed integer programming with some constraint programming in there as well. So some examples. Project scheduling. We have a series of operations required to complete a project, like building a bridge. Each operation requires some resources. Now you need to schedule the operations on the resources. There might be some temporal relationships between the operations. This operation can't start before another one ends. You need to schedule these on the resources to finish your project, meet the due dates in your project. Manufacturing, okay, specialization, project scheduling, series of operations, or manufacturing assembly line, this is a truck, okay? Resources required, you need to assign operations to resources over time in order to find the shortest schedule, in order to maximize your on-time delivery. So this is really industrial. Mentioned airport, okay? So an airplane lands, what do you have to allocate? Well, it needs a runway to land on. It needs some taxiway to get to a gate that you've also assigned. It needs a baggage carousel, security personnel to meet the plane. You need ground personnel to meet the plane and bring it in. You need to refuel, you need to restock, and you need to turn the plane around quicker, right? They want to be on the ground less than 25 minutes if they can, because if the plane's on the ground, it's not gaining any money, it's not earning any money. And think about the connecting flights. You want to schedule your flights so that connecting flights are close together, but not too close together, because there's going to be some uncertainty and lateness. So there's going to be some sort of optimal time between connections, between frequent connections. If you think about modeling people, modeling the types of preferences they have for the trips they tend to take, there's a big data side of this to understand how you're going to come up with the schedule and then how you're going to allocate the gates, because you don't want them walking from one end to the other of the airport with a 15-minute connection time. And, oh, by the way, a new plane lands every minute. Okay, and you've got weather problems, you've got all sorts of interesting online, uncertain things that are going on with airline scheduling. So there's actually a big series of scheduling problems here, based from a strategic level where they're actually defining the routes, to the tactical level where they're putting staff on the planes, trying to figure out how the staff is going to get back to where they started from, depending on the legs of the different flights that they're on. And then you have the online, when something goes wrong, when there's a weather delay, how do you reestablish your schedule? There's a lot of stuff going on here. Workforce scheduling. Okay, anybody who's ever worked in retail, you've been scheduled, right? When are your shifts? When do you have to be there? When are your breaks? Oftentimes, if you're in a good position, there are union regulations about the amount of time you have off, or the amount of time you can work without a break. Okay, so you have to take into sometimes complex regulations in coming up with schedules for the people. Examples in nurse scheduling, call center scheduling. Whenever you're scheduling people, there's often an interesting scheduling problem. All right, so from that high level, we're going to go to the fruit fly of the scheduling world. So this is the job shop scheduling problem, which is the one that this is the one that has been studied the most in the literature. The schematic diagram here is we have operations, or tasks, or activities, and I'm going to use those interchangeably. The length of this task is supposed to indicate its duration. Okay, so this is somehow time, and so this operation is longer than this operation, this one is shorter than those two. This is a precedence constraint, meaning this operation cannot begin until this operation has ended. So think about the manufacturing context, where you've got some raw materials, you have to do some transformation, do another transformation. This transformation can't start before this one ends, and you move the material from one machine to another, for example. I've compiled the resource requirements into colors. So in this case, the red jobs, or the red operations, correspond, they need to be assigned to the red resource. The green ones are assigned to the green resource, and the blue ones are assigned to the blue resource. So now we don't have a resource choice. We know in the classic job shop scheduling problem which resource each of the activities needs. And this whole thing is called a job. So a job is made up of a set of operations typically connected in a linear fashion in the classical job shop scheduling problem. And what we're trying to do is we're trying to come up with a schedule. Okay, so now I'm looking at what's called a Gantt chart. Each of these is one of the resources. And what I need to do is I want to minimize the make span, the time from the beginning of the schedule to the end of the schedule, subject to the precedence constraints. So I've just drawn in the precedence constraints from this first job here to show you that the precedence constraints are satisfied for that one. The rest of them will make a big mess of my drawing. And I've satisfied the resource constraints. So in the classical problem, the resource can only do one thing at a time. And what that means is essentially we have to have all these green activities have to be sequenced in some sequence. Okay, red has to be sequenced, this has to be sequenced, so that these precedence constraints are satisfied and we've minimized the make span. So that is the job shop scheduling problem, the classical one. And of course, we have complications. If you think about the earlier problems I've been talking about, resources can be continuously produced and consumed. So think about a pharmaceutical or a chemical situation where you're producing some material into a tank, and you can feed into a tank and suck out of the tank at the same time. Okay? Batch resources. If we have an oven, we're going to typically want to turn on the oven and bake something for however long, but we can put multiple things in that oven as long as they respect, they need the same temperature requirements. And so this is sort of a resource where a bunch of these jobs might come together. Rather than having one action at a time in this oven, we can put a bunch of things in this oven at one time, right? And so if you think about this, well, maybe these guys need to be at the same time, right? Because so now we have some sort of concurrency constraint, or might not be a constraint, but it might be good if we can put them in the oven at the same time. Sequence-dependent changeovers. So if you're scheduling a factory that makes food, it makes dog food and it makes people food, okay, well, when you transition from dog food to people food, you probably want to be fairly careful about cleaning out the machines, right? When you translate from people food to dog food, probably doesn't matter that much, right? And so the transition, that is the time from the end of one activity to the start of another activity, can depend on the identities of those two activities. And the reverse might have a different transition time between them. Okay, so cleaning is a classical example of a sequence-dependent changeover. You can get much more complicated optimization criteria, some cost-based, some due date-based, and in general, multi-criteria optimization. The durations of these guys, well here, they're fixed. I know that this operation is going to take this amount of time, but if I have an option of placing these activities on different machines, maybe I have faster machines and slower machines, and so it might be that the actual duration of my activity depends on the machine to which it's assigned to. All right, a key difference to planning, the key difference to planning. In scheduling, we know all the operations that we need to schedule. So we are given a set of activities, we are given the temporal constraints between the set of activities. We do not have to reason causally that this activity must be before that activity due to the way they change the world. If this activity has to be before that activity, we've got a precedence constraint. If there's no precedence constraint, there's no requirement that they have to be in any particular order. So we're given all these things. Whereas planning, obviously, we're instantiating the operators to figure out what are the actions that are going to have to take us from our initial state to our goal state. You can think about the planning problem that's been done for us. We have a set of these operations that we need to schedule. In some formulations, we may choose not to schedule all the operations. So we might have optional operations. But typically, in our problem, we are never going to have a decision that will add a new activity. Okay, we might be able to decide some activities are going to be ignored, but we're not going to add them in the classical, in general scheduling problems. It would be very strange to have new activities arriving based on our sequencing, based on our search decisions. Okay, a difference with the planning and research. So we actually publish papers on the job shop scheduling problem. Okay, so that's like publishing a paper on the logistics problem. Nobody's really interested in planning in solving the logistics problem, but people are interested in solving the job shop scheduling problem. Okay? There is still a desire to be domain independent. Right? We don't want to have a different algorithm. I change my problem a little bit. I change my cost function, and suddenly I have to throw everything away and go back to something new. But it's more bottom up. Okay, so we take techniques that work on job shop scheduling problems. We build them into a solver, for example, a CP solver, okay, and apply them to other problems. And this comes in through modeling. So constraint programming solver or mixed integer programming solver is a very general solver for combinatorial optimization problems. We can specialize, we can apply them to scheduling problems by modeling that scheduling problem. By taking the real world problem that's out there, by making the appropriate abstractions, because we're not going to represent everything. But what we have is a mixed integer programming model for a scheduling problem. We might have different mixed integer programming models that use different variables and work better or worse than each other. Okay? And so there's a significant amount of work on modeling of problems, even modeling problems like job shop scheduling problem, which you wouldn't think to have a whole lot of different models that are possible. Well, there are. There are at least 4 different mixed integer programming models recognized in the literature for the job shop scheduling problem. And so this is at a different level in terms of the domain independence, right? CP and MIP solvers, a MIP solver will solve any problem that has integer continuous variables, linear constraints, and a linear objective function. Okay, if you've got a problem like that, you can throw it into a MIP solver. It might not solve it because of the size of the problem, right? It's still an NP-complete problem, so your mileage may vary. But you've got very strong commercial solvers that can solve a significant, a surprisingly large array of completely different problems that are represented as mixed integer programs. Similarly with CP, we have these generic solvers that can represent scheduling problems, routing problems, staffing problems, any type of problem, many types of problems. And then you throw it into a generic solver, and in many cases it works surprisingly well. So the domain independence is at a different level, where it's there, but at a different level because of this strong modeling work that we do in the scheduling and optimization community, which is something we should do more in the planning community. In particular, the model is not the problem. Okay, that is, we have some real problem out there, and we have maybe multiple mathematically equivalent models of that problem that we devise and experiment with. Whereas in much of the planning community, the model, that is the PDDL files, is the problem we're trying to solve. And people don't start thinking about, well, this PDDL model is better than that PDDL model of our underlying logistics problem. Okay? That would be interesting, right? If we take these models, different PDDL models of the same underlying problem, understand how they perform, what makes one model better than another. I think this is something that the AI planning community needs to get into. That's enough of that rant. Okay. So I'm going to talk about exact solution techniques, focusing on first CP, and then a bit on MIP, and then into my decomposition. One note here is I'm ignoring meta-heuristics. Those of you who know about meta-heuristics, Taboo Search, Simulated Annealing. There are thousands of papers on solving scheduling problems with meta-heuristics. I'm not going to talk about it. So this is what we saw earlier, the secret sauce. And so the other thing we talked about was our consistency. So this is just to remind you what we talked about. Our consistency means we can remove values from domains of variables if we can prove by reasoning locally, let's say about a constraint, that this variable cannot satisfy this constraint. This is the same thing we're going to do in scheduling. This is our global constraint. Okay, this is our definition of a global constraint. And if we think about what's going on, well, if we want to solve scheduling problems, what we're going to do is we're going to start inventing global constraints for scheduling problems. And we're going to understand what they are. We're going to invent some inference algorithms that will do the inference given a scheduling problem, or given a piece of the scheduling problem. All right, and that was my definition for generalized R consistency. Remember, we're over some arbitrary but fixed number for a given problem of variables, and what we need to do is we need to find a support, which is essentially a solution to the entire constraint in order to justify that this value will remain in the domain. Okay, job shop scheduling. Here's an example of what's the workhorse of CP scheduling, which is the cumulative constraint. The idea is the following. We've got time along the x-axis, and we've got capacity along the y-axis, and this line is supposed to indicate this is the maximum capacity on this machine. These guys are activities. Okay? The length of the rectangle corresponds to the duration. This orange thing represents the time window within which that activity must execute. Okay, so this is the earliest start time of this purple activity, and this is the latest finish time of that purple activity, so you can imagine that it can slide between those two within that interval. The vertical here corresponds to the amount of this resource requirement for this activity. Okay, so this activity must execute between this time and this time. It's going to execute for this duration, and during this duration, it's going to use that much of the resource. So one of the things you might think about here is maybe this is a team of people. Okay, we've got 10 people, and we can place them on, this uses 7 people, this uses 3 people, and as long as we can allocate those people so that the sum of the people being used to do those operations at any given time is less than or equal to C or 10, and we've got a schedule. All right, so the idea is, what does generalize our consistency mean for this constraint? Do you have any idea, given what generalize our consistency means, what would we try to do if we were going to try to do inference and try to figure out how to pose generalize our consistency on this cumulative constraint? How would you model this as a CP problem? Start with the variables. Somebody give me a reasonable variable. What would you represent as a variable? Yes?
The start and end times.
So it could be the start and end times. That is, we have a variable that represents the start time of an activity. Okay, that's one thing we could do. Any other ideas? Remember, we're talking about different models for the same problem. Okay. What if C equals 1? So rather than having a cumulative constraint, we have what's called a disjunctive constraint. If C equals 1, what would be another variable that we could use to represent this problem? Or a piece of this problem?
The consumption of the weight sources.
So it's certainly the case that sometimes these activities don't have a fixed amount of resource. Sometimes they could consume more or consume less. Okay, but we're going to assume now that each activity has a fixed amount of resource. And if this is equal to 1, then each of these activities requires only 1 unit of that resource. So think about the job shop scheduling problem and the solution to a job shop scheduling problem. What did I say a solution to a job shop scheduling problem was? Yep.
The order of activities.
The order of activities. Okay, so what do you want to do for, if that's the solution, what do you want our variable to be? So you could introduce a variable for every pair here. That specifies their sequence, right? Xij equals 1 if I is before j, Xij equals 0 otherwise. Okay, and so if this were a disjunctive resource, we might want to represent it not as start time, but actually represent it as a sequencing or an ordering variable. Okay, and if you think about it, we can actually take a solution. If this is, again, capacity of 1, you can always transform a feasible solution on the ordering constraints. In polynomial time, you can come up with the start time variables. Okay? But let's talk about the start time variables. Okay, so if I have a start time variable, I need a domain of the start time variable. The domain of the start time variable, well, let's say given this interval, okay, the domain of this start time variable, this is going to be the earliest possible value. The latest possible value is going to be this minus the processing time or duration of this guy, right? So now you can imagine this interval, which corresponds to the domain of the start time variable of each of these guys. That is the earliest start time, latest start time. Okay? Now we're going to talk about doing propagation, right? Doing GAC. So what we want to do, if we're doing full GAC, is every element of the domain of the start time variable should participate in a solution to this constraint. That is, there should be some schedule of this set of activities that will guarantee, that will satisfy the time windows, satisfy the capacity constraint. Typically in scheduling, we do something weaker. We don't worry about arc consistency, we worry about bounds consistency. That is, we're only really worried about the earliest start time, latest start time, and we prune by shrinking these domains rather than working in the middle. Okay? Unfortunately, even if we're just looking at bounds consistency, generalized arc consistency for this constraint is NP complete. So unless we're actually solving a problem that's as hard as our original problem, we are not going to be able to build a propagator, build an inference mechanism that's going to guarantee generalized arc consistency. And in that case, what we're going to do is we're going to do it anyway, but it's going to be some sort of approximation of generalized arc consistency. That is, what we're going to do is we're going to come up with polynomial time algorithms that will do some of this pruning, that will remove values from the variables where we can prove this value does not participate in any solution. But it's incomplete in the sense that there will be values in the domains of our variables which do not participate in a solution to this constraint. So they're not locally consistent, and therefore they're not globally consistent, or they perhaps are not globally consistent. But we can't detect all the locally inconsistent variables unless we're willing to solve an NP complete problem. So we're never going to remove values that participate in a solution here, but there will be some values that we do not remove that do not participate in the solution. So here's an example of one of the most important propagation algorithms, inference algorithms. We're going to talk about the unary capacity resource. So everything here has to be sequenced. This is a set of activities called S. These numbers represent their durations. ESTS is the minimum of the earliest start times in S. That means the minimum earliest start time of all these guys is 10. LFT is the latest finish time of S. So that means all of these guys have to be scheduled between 10 and 80. Yep?
Do you ever consider the problem where it's allowed to split them up? I mean, it doesn't make sense if all the capacity is the same, but...
Yeah, so you mean you can start this activity, stop it, do something else, and start it again?
Yeah, I
Yeah.
mean, it doesn't make sense if they all have the same resources, but...
Well, it does make sense. That's called preemptive scheduling, right? And so I'm going to be talking about non-preemptive scheduling. If you start an activity, you have to run it till it's finished, okay? There is another version of this where you are allowed to preempt. That is, you can start, stop it, run something else, and then do something else, and it has some different mathematical structure to that. But I'm going to focus on non-preemptive, okay? Okay, so look at this guy. We've got a time window of 70. We've got a sum of durations of 60. So without any other information, everything looks fine. Okay? And now we have this guy. This guy has a duration of 25, can start at 0, and can run to 100. Now what we can actually do, and this is actually completely non-obvious if you get into the details of this, at least it was to me, we can actually figure this out. Simply by propagation, we update the earliest start time of this guy to 70, and therefore its latest start time to 75. So now we've got a reduction of the size of 100 down to 5. And the latest finish time of all these guys is reduced from 80 to 75. Okay? And the reasoning is as follows. I'll show it to you this way, right? If you think about this guy, if you run this guy before everything in set S, it's going to start in the best case at time 0, and at time 25, plus 60. 60 plus 25 is 85, but all these guys have to end by 80. So this guy can't go before everything in here. If we try to run it in the middle, we've got 60 plus 25, 85, but we've only got a time window of 70, so there's no way we can run it in the middle. Can't run it before, can't run it in the middle, we have to run it afterwards. And that afterwards is the earliest start time, plus the sum of durations of all these guys. This guy cannot start before time 70. Similarly, this guy is running from the latest it can finish is 100. That means the earliest it can finish is 75. That means all of these guys need to finish by 75. So again, we're reasoning about the fact that all of these guys have to end up in a sequence because this is a unary capacity resource. And this is a very significant amount of propagation out of inference we can do. We can do something, there's a generalization of this for a non-unary capacity resource. just to show you what it looks like, okay? So this is the time window of the set S, right? Latest finish time minus earliest start time. If that guy is less than the sum of the durations, the sum of the durations of all the activities in S plus the duration of A, that is my top activity. This means if the set union A does not fit into the time window of S, because this guy is the time window of S, and if A does not fit before S, okay, because the time window of A before S is A starting at its earliest start time and everything else finishing by the latest finish time. If that also does not fit, then the earliest start time of A has to be the earliest start time of S plus the duration of S. Okay? Now, what's the problem with this? There should be a big, ugly problem right here. Why is this terrible? Why is this completely ridiculous and will never work? Give anybody a hint? Pardon me? I didn't hear you. I have to do some computations here. How many times do I have to do this computation? Based on what I wrote down, I have to do it for every non-empty subset of S. Okay? There's an exponential number of those. This is terrible, it's useless. Okay? The fundamental breakthrough is you can actually do this in log n with some nice data structures. Okay, there's a long story behind this. For a long time, the best known algorithm was n squared, even in the commercial software. Well, sorry. The best known algorithm was n log n. The best known algorithm that anyone except the authors could actually implement was n squared. And so the algorithm that was in the commercial solvers was actually n squared, because no one could actually successfully reproduce the algorithm, the n log n algorithm that somebody had published. A few years later, Peter Willem came up with an understandable n log n algorithm with a very nice data structure, and so that's why we can now confirm that it is indeed n log n. What that means is the amount of inferences you can make by considering each non-empty subset is equivalent, same strength of inference, where you only have to do it n log n times the carefully selected n log n. So there's some very nice work here. All right, there's a whole bunch of research here. Cumulative constraint propagation, I even did some work on it. Other constraints for scheduling, okay, setups and TSP, so if you're doing those sequence-independent setups, that starts to look like a traveling salesman problem, right? The transition between the end of an activity and the start of another one looks like a TSP. So there's some work on the assignment problem in TSP for setups. Other stuff. And heuristics for scheduling. My whole PhD thesis was based on heuristics for scheduling. It was too long ago, so you shouldn't read it anymore. But there has been people who have worked on heuristics for scheduling. So let's talk about modeling. Okay, so I'm not going to talk about the details of the algorithms anymore. Okay, we're assuming we have techniques for doing branch and search, assuming we have all these a number of great global constraints to do the inference. Let's talk about the models. So this is a job shop scheduling model. We're going to minimize the make span, which is traditionally represented by Cmax. Sj is the start time of, in this case I'm using job, I should use operation. It's the start time of operation J. And what this is saying is all the operations need to end before the make span, and each operation can start at time 0 or later. This is a precedence constraint. If you go back to the picture, remember I had a job, which was, in our case, 3 operations with a precedence constraint. So there's a precedence constraint in the job. When there's a precedence constraint in the job, I have to say that the start time plus the processing time of the predecessor needs to be less than or equal to the start time of the things that's the successor. So in this case, the precedence constraints are predefined because they were there in the job. This is the global constraint. Okay, this is the disjunctive constraint. This is the specialization of the cumulative constraint that does edge finding and all those great things. It takes the variables, which are the start times, and it takes the processing times, and what it does is inference, pruning those start time windows based on reasoning such as edge finding. So this is the entire drop-shot scheduling model. All right. How many people know what mixed integer programming is? Number of you? All right. So this will be boring for some of you, but I'll do it quickly. So it is really the most successful complete optimization approach. So it is really running in a whole lot of the industries that are out there. There are at least 3 quite successful commercial solvers that are being used. It comes from the operations research applied math community, starting in sort of the 40s and 50s, and has been developed to quite a high extent, much longer history than we can right now. The basic idea is as follows. Okay? We have an objective function, which is a linear constraint. Okay, so V is our set of variables, and we've got a constant, which could be integer, could be a real number. What we're doing is we're summing over a weighted, creating a weighted sum of variables, and we're trying to minimize. Okay, these variables can be integer, right? VI are integer variables, VR are continuous variables. Our constraints are linear constraints. Okay, each of these is the sum of a coefficient times a variable value is less than or equal to some sort of right-hand side, and this guy can be less than or equal to equal or greater than. Okay, this is a mixed integer program. And the really cool thing about mixed integer programs, so in general, a mixed integer program is NP complete. It's used to model problems that are NP complete. If we throw away this, that is, we don't throw away the variables, but we throw away the constraint that some subset of the variables have to be integer. That means I've got a set of continuous variables, a set of linear constraints, and a linear objective function, and this is polynomially time soluble. Okay, this is a linear program, and we can solve it in polynomial time, and there are about 5 or 6 well-known algorithms, simplex being one of them, dual simplex being another one, that will solve this problem in polynomial time. This is the core fact that makes mixed integer programming solvers work. Everything about mixed integer programming solvers, pretty much, is based on solving this relaxation at each node in our search and exploiting the solution to that relaxation to do branch and bound, to generate new cuts that are new redundant constraints that tighten our relaxation. So everything pretty much surrounds the linear programming relaxation. So here's a visualization of the techniques that we're going to use to solve this. So we've got a 2-variable example here. Okay, x1 can take the values 0, 1, 2, 3, x2 0 to 5, and these points indicate that x1 and x2 are both integer variables. Okay, here are a set of linear constraints, which in this 2-dimensional example give you a 2-dimensional polygon. Okay, and hopefully you can realize that, well, here's a constraint. This constraint says x2 is less than or equal to 4. Okay, we have our objective function here, and that arrow shows that we're trying to maximize the objective function in that direction, right, in the direction that's orthogonal to the actual linear expression that represents the objective function. And so we know that a solution to a linear program is going to be one of the vertices of the polytope. Okay, so this thing is called a polytope in multiple dimensions, if you think about it more than 2 dimensions. We know that when we ignore the integer constraints, the optimal solution is going to be one of the corners of our polytope. And in fact, some of the algorithms like simplex are based on the fact simplex actually moves around from point to point in an intelligent way to maximize the objective function, from vertex to vertex. So, what do? We find a corner that maximizes the cost function using a polynomial time algorithm. stories, but simplex is not actually polynomial time. Okay? The underlying problem is polynomial, but we're actually running an algorithm in most cases that is not polynomial, because in practice it's much faster than many of the other polynomial time algorithms that are used. In any case, this is a polynomial time problem to solve. And if this point is not integer, we need to branch. And so a typical way to branch is to add a constraint. We're going to add this constraint, okay, which is x2 is less than or equal to 2. And then we're going to focus on this region. So this is a branch in our search tree. We've added the constraint x2 is less than 2. And now we're going to focus on here. Later, after we found a solution here, or not, we're going to backtrack and follow this constraint, which is x2 is greater than or equal to 3, which will limit us to this region, and we'll again search for a solution in that region. So our branching can be seen as a partition, as we're introducing, in general, a plane that cuts our polytope into sections. Anything that's not in here, right? There are no solutions in here because there are no integer values for this variable, for x2, in between them. Okay, so we're not missing a solution because of the way we branched, because we're less than or equal to 2 or greater than or equal to 3. So we do that. Now we focus here. We run our simplex algorithm again. We find the optimal point. I'm not going to talk about what this is, but there are forms of inference that are used in mixed integer programming to actually realize, well, we can, in some cases, we can tighten the bounds on the variable, and so we can apply that at a root node and resolve, and now our LP has magically ended up at an integer point. Okay? And one of the great things about an LP, since it's a relaxation of our integer problem, if we end up with an LP solution where all of our integer values have integer, all of our integer variables have integer values, we found the optimal solution in that subspace. Okay? So we don't have to keep going, we don't have to keep searching through here and end up with an assignment for every variable, because our LP solution has given us integer solutions, integer values for our integer variables. We do, however, need to backtrack. Before we backtrack, though, we've just found an incumbent solution. This is a feasible solution, but it might not be optimal. However, we can use it because now we're only looking for solutions that are better than this guy. So in particular, we don't have to look at this piece, right? Because this piece, if there's any solution down here, it's going to be worse than this solution because the better solutions are up there. And so now we're using this new solution to bound our search, to cut off a piece of our search space that we don't have to look into, because if there exists a solution, it's worse than the one we've got. So now we go over here, find an optimal solution, do some bound strengthening, do it again, here's our new solution, and in fact we're done. Now, there was a bug in the slide. This is not the optimal LP solution. This is the optimal LP solution. But usually, if I have more time, I would ask you to find the bug in the slide. All right, now we're done. So, what I've just shown you is called branch and bound search. Okay? There are all sorts of sophisticated things that have been developed over 40 plus years of mixed integer programming solving. Branching heuristics, how do you branch? How do you choose a variable to branch on? What are the constraints you add? Cutting claims, which are a form of inference. Primal heuristics, which what that means is at a node in my search tree, I might spend some time trying to find a feasible solution. Okay, I can run some local search techniques, I can run things that look a little bit like genetic algorithms. A lot of MIP solvers have a lot of black magic in them, but primal heuristics that can quickly find a feasible solution is one of those pieces of black magic, because once you find a feasible solution, you can do things like this, right? You can use it for bounding, which is going to significantly remove pieces of the search space. So there's a whole bunch of black magic going on in there, how you do backtracking, etc. All right, back to our drop-shot sketching problem. So here is a disjunctive model for a drop-shot sketching problem. So focus down here, set ij is 1 if operation I is scheduled after operation j. So we're using that ordering variable that we talked about earlier, which we can use in CP as well. Okay? Cmax is largest end time, nothing new there. Okay, this is we're going to minimize Cmax. This is the same constraint we saw in CP. This is the same constraint we saw in CP for those precedence constraints that are in my job. Those are precedence constraints. And this is the resource constraint. Remember in CP we had this strange thing that just said disjunctive. And there was some black magic inside of there, i.e. an inference algorithm, that took care of that constraint. Here, we don't have that luxury. Everything here has to be a linear constraint. And so we need to somehow figure out how are we going to represent a disjunction with linear constraints. Think about it. It's kind of difficult. Okay, so this is one of the tricks. To do it, it's called a big M constraint. So if you look at MIP models, you'll often see big M constraints. They tend to be horrible models because these constraints use a very large number here and tend to make the linear programming relaxation very weak. So the relaxation is going to be far from the optimal solution. And since the relaxation really drives everything here, having a loose relaxation is an indication that your model is never going to find the solution. However, somehow we've got to represent this. So let's talk about what this is. So ZJI is 1, means operation I is after operation J. So let's look at this guy. Okay. If ZJI is 1, then what we're doing is we're taking the end time of I, and we're subtracting a very big number. Okay, so this guy, this right-hand side, is probably going to be negative if we pick n big enough. It should be negative if we pick n big enough. And therefore, since minimum value for Sj is already 0, what we've basically done is we've turned off this constraint. Right? By making this 1, this subtracts a big negative number, and this constraint becomes non-binary. Okay? In contrast, the same way, this guy is 1. So 1 minus 1 is 0. So this is now 0. And we've enforced the constraint that I is after j. The start time of I has to be greater than or equal to the end time of j. Okay? And vice versa, if this is 0, we get it the other way around. Okay, so this is the core way that we represent disjunctions in mixed integer programming. There are some more sophisticated ways, but this is important. And just to show you what happens, okay, here is the disjunctive MIP model. This is a set of 10 20 by 20 drop shop sketching problems. 20 by 20 is basically beyond the state of the art in terms of being able to find and prove optimality. This is the percent above the best known solution, so lower is better. Here is an out-of-the-box MIP model using Cplex, which is one of the top solvers. If we run it on 8 threads, we get better. If we train it on the test problems, so as we have these 10 instances, we told Cplex we're going to run you on these test instances, so we're training on our test problems. So we're trying to give Cplex as much help as it can. It improves it a bit more. Okay, this guy is CP out of the box. Okay, and this guy is a hybrid algorithm that uses having search for a while and then switches over to a more customized and sophisticated CP solver. The customization comes from some of the branching heuristics we're doing. And so you can see that in terms of a complete solver, CP is pretty much the state of the art for drop shop sketching problems. And if you look at how these guys are evening off, MIP is not going to cross over with CP. So there's some of this. So this was just to show you that CP is actually the state of the art, or certainly a competitive state of the art algorithm for scheduling. Okay, now I'm going to talk about some decomposition approaches. Take a big ugly problem and break it into subproblems that can be handled. So this is a very common technique. Often when you're faced with a real world problem, it's too big and ugly, you can't come up with a single CP model or MIP model. You need to start cutting it up into pieces, solving that piece, perhaps the optimality, using that solution, coming up with a model for the next piece, solving that, and you go down the line. You've lost global optimality. Each of your pieces is locally optimal, but you have no guarantees. Okay? Now, we can also do decomposition with feedback, where we create a decomposition, solve, let's say, the master problem, which gives us some subproblems, and then based on the solution to the subproblem, we can feed back some information to the master problem and solve it again. And if we do this in a clever fashion, we can actually get some exponential speedups while not losing our optimality guarantee. And there was a whole master class at CPAOR about a week ago that talked about decomposition techniques within constraint programming and mathematical programming. So, losing optimality is bad, but you can sometimes maintain it if you're clever. So, I'm going to talk about logic-based Bender's decomposition and then give you a couple of examples of that. Here's our global model. So you can think of this as the job shop scheduling problem that I just produced. Okay? Actually, it's not very useful to think about it as a job shop scheduling problem because I don't know how to decompose a job shop scheduling problem. Think about it as a more complicated scheduling problem, but I've got some monolithic CP or MIP model that will solve that problem if given infinite amount of time. What I'm going to want to do is I'm going to take this problem, take this model, and I'm going to relax it. So I'm going to throw away some of the constraints, perhaps some of the variables, and create a master problem. Okay, in fact, project the problem onto a subset of the variables, which are going to be the master variables. I'm going to solve this problem with CP or with MIP to optimality. And then based on the solution to this problem, I'm going to create one or more subproblems, which bring in the variables and constraints that I relaxed from up here. If I'm lucky, I get more than one subproblem because there is some way to decompose things. So if you think about the multi-agent planning stuff that Ronan was doing and this global-local representation, this is what we're doing here. Okay, we have some global representation, right? And after we find a solution, we might be able to solve each of these subproblems independently and glue them back together. In this case, we're going to actually not simply hope we can glue them back together. If each of these guys, let's say, is feasible, let's say these are feasibility problems, I have an optimal solution to a relaxation. Each of these guys is feasible. I have an optimal solution to my global problem. If one of these guys is not feasible, what happens is I generate what's called a cut. I don't know if you guys can see these arrows. This is an arrow from here to here. This is an arrow from here to here. This is a new constraint. The subproblem derives a new constraint that is broken by the current master solution. So the master solution doesn't know everything about the problem, because some of it is hidden in here. I've given a solution to this subproblem. The subproblem realizes this is not a global solution because of something it knows, and it compiles that knowledge into a constraint for the global solution that basically says, here's a constraint that's broken by your current solution. Give me something else. This constraint then gets incorporated into the master problem, and the master problem resolves to find a new solution. And so what we're going to do is we're going to iterate here until such time as the master problem solution is feasible in each of our subproblems, and we have a proof of optimality. This is interesting because we're never working, so we're always working in the infeasible space, right? The first globally feasible solution we find is optimal, because every solution before that one breaks one of our subproblems. So it's an interesting idea that we're working in this infeasible space rather than the standard way where we find solutions that are generally gradually increasing. Here we're always working in the infeasible space until we find the first feasible and optimal solution. And the proof of optimality comes from the things we've been doing all the way along. There's no global proof in the same way as branching back. All right, so I'm going to talk about two of these problems, I think. I'll see how it goes. So this is the simple problem, resource allocation and scheduling, and hopefully this will be the simple problem that makes concrete this decomposition and the ideas about these cuts. So I'm imagining I have the resource allocation and scheduling problem where I have a set of these operations or jobs. They have no relationship between them in terms of temporal relationships. Okay, so there are no temporal constraints here. Each of them could be assigned to one of three machines or factories. So one of the decisions we have to make is, which of these jobs goes to which of these machines. Once that decision has been made, however, because there are no relationships between these guys, each of these scheduling problems is independent. These jobs might have different processing times and different resource usages depending upon which of these machines they're assigned to, and they also have time windows. So there is a minimum start time, latest finish time. So simply, this guy, even with a unary capacity resource and time windows, is an MIP complete problem. Okay, so these sub-problems are still hard to solve. So what are we going to do? Each job has a release date, which is an earliest start time, and a deadline, which is its latest end time, so that's that window. A processing time, PJK, which is different, or potentially different, depending upon the resource it's assigned to. It has a resource requirement, RJK, which again, potentially different, depending upon the resource it's assigned to. And it has a cost, CJK, the cost of assigning job J to resource K. This is actually a fairly simple cost structure, because all I'm going to do is minimize the sum of my assignment costs, subject to having feasible schedules on each of the machines. Okay? So we want to assign and schedule jobs to minimize the total assignment cost while satisfying the time windows and the resource capacities. Any questions about this problem?
Yes, one. One job can have time free for the resource number 1 and 5 for resource number 2.
Yeah, and there's no necessary relationship amongst them, so one job can be 3 and 5, another job can be 10 and 2, so it's not like one machine is necessarily faster or slower. There's no necessary relationship there, okay? All right. So, here's a CP model for the whole problem, okay? We're going to use xjk, this is a 0, 1 variable, which is 1, if job j is assigned to resource k. If we sum over, that is, for a given job j, if we sum over the resources, exactly one of them needs to be a 1. Okay, we need to assign a job to one resource. We can't assign it to multiple resources, and we can't assign it to 0. This is my wonderful global constraint that's called op cumulative, which is a variation of the cumulative constraint, which takes into the account these xjk variables. That is, it takes into account that this activity might not be assigned. So if you think back to what we did in the first part, where there was that in-plan constraint in the CPT model, this is a similar constraint inside the op cumulative, because we might decide not to schedule job j on resource k. An op cumulative is a generalization of the global constraint, which takes into account the fact that it can only do the reasoning. Well, it needs to take into account that optionality when it does the reasoning. And this guy's a time window. Okay, the start time of an activity has to be between its release date and the maximum of its due date minus its processing time, depending upon which resource it's been assigned to. PJK changes. Okay. Tends not to work too well. Anybody give me a guess about why it tends not to work too well? Constraint programming works when what? What's the secret sauce? Everyone's asleep. So, inference, right? Constraint programming lives and dies on inference. Why might inference not be very useful here? Or might not work very well here? So think back to the edge finding example, or that cumulative constraint example, where I'm pruning time windows based on the durations of the other activities. At my root node of my global search, none of these xjk variables have been assigned. If I could have no jobs on a given resource, or let's say it in a different way, if I have a particular job 1 on a particular resource, and all my other jobs on that resource are optional, I cannot make any inferences about the time window of that job, right? Because the inference says, well, if this other job is here, this one can't go here, but this other job might not be here, okay? And so if you think about what's going on here, even if I assign all these xjk variables first, I'm going to be pretty deep in my search tree before my cumulative constraint is going to start pruning my search windows, my start time windows. Okay, I have to do a bunch of decisions with no feedback, with no propagation, before I'm going to finally get to a point where I can start propagating. Because if everything is optional, I can't make any inferences. Here's a time index model. Okay, so I talked about this disjunctive model. This is a time index model. Okay, and the core of the time index model is this guy, which we'll get to in a second. So actually, let's talk about this core variable. It's the same variable here. So this y, kjt, says job j starts at time t on resource k. And what this is saying, this is what's called a channeling constraint. Won't go into the details, but this guy is the same constraint we saw before, xjk, so we have to assign a job to a resource. If I don't assign a job to a resource, so if this guy's if for a particular j and k this is 0, then the sum of the start time variables of that job on that resource had better be 0. If I haven't assigned it to the resource, it better not start on that resource. If on the other hand it's 1, well, exactly one of those start time variables has to be 1. Okay, so this is a 0, 1 variable, and I have a 0, 1 variable for each job, for each resource, for each time point. So that's why it's called a time index model, because we're indexing the time to these Boolean variables. However, if you think about the disjunctive model, and you think about the fact that we've got a cumulative constraint, it's kind of difficult to figure out how you can do disjunction with a cumulative constraint. Okay, so a disjunctive model is not going to work here. So we have to do this time index model. We try to avoid time index models as much as we can in scheduling, because now the algorithm scales with our granularity, as with the number of time points we have is going to make this model very large. And typically, this will fill up memory before we can actually get a reasonable size problem. So this connects the decision about which resource to assign with our start time decision. This is our resource capacity constraint. I'm not going to go into the gory details here, but basically what this is doing is this is summing up the start time variables to make sure that at every time point they're less than or equal to the capacity. This is a resource relaxation. What this is saying is for every job that must execute between time t1 and t2, processing time times its resource requirements. So this is the area of the rectangle that I've been using to represent the activities. So this is going to be the sum of the areas of the jobs assigned to resource k. That must be less than or equal to the total area available on resource k, which is the time times the capacity. And is there a picture of that? Okay. So, those were two monolithic models. Here I'm going to do a master problem model. Same cost function. Same resource assignment. This is going to be my subproblem relaxation, which is just what I explained to you for all the jobs assigned to a resource, okay, where some of their areas has to be less than or equal to the area that's available. And this is what's called a Bender's cut, which we're going to talk about in a couple slides. So, the subproblem relaxation is what I just hand-waving told you about. If I take the sum of these areas, all these guys are assigned to the same resource. Well, I know that this time window times this capacity, this area must be greater than or equal to the sum of these guys. Otherwise, there's no way I'm going to be able to pack them on. it's a relaxation, this might be true, and I still might not have a schedule, okay, but it is a linear relaxation here. The bender's cut, so this is the constraint that comes back from the subproblem to the master problem. So what's going on here? This is a counter for my iterations. So every time I solve a master problem and subproblem, that's an iteration. This guy is the set of jobs assigned to resource K in iteration H. And what is this saying? So this is a variable in the master problem. So I'm summing over the set of jobs that I was given on the subproblem, that I was given in iteration H. By definition, because I got the jobs, the xjk variable is 1. Right? In my master problem, xjk variable for every variable that was given to me on resource K is assigned to 1. So what this is saying is at least one of the jobs that you gave me needs to be assigned someplace else. Right? So do not allow the same assignment of activities or a superset to be assigned to the same resource. So what I've done is looked at the set of jobs assigned and added this linear constraint. Every subproblem that is inconsistent adds one of these linear constraints to the master problem. And our subproblem's easy. We don't even have an objective function, so it's just feasibility. We have the cumulative constraint. It's not opt-cumulative, because at this point, everything's been assigned to me. So I know everything's going to be here. My master problem, sorry, my subproblem doesn't have any optionality left to it. This is going to be a good problem for constraint programming because inference is going to work right from the beginning. It's a single machine, cumulative feasibility problem. And of course, my machines are all solved independently because there's no interaction between the jobs. So, to make this type of decomposition work, we need some sort of subproblem relaxation in the master problem. If you think about what the master problem is doing, it's coming up with solutions. If it knows nothing about the constraints that have been removed, it's going to wander around in the dark and say to the subproblem, is this good? Is this good? Is this good? And so what you want to do is you want to somehow build a relaxation of the subproblem, of each subproblem, into the master problem, so that it doesn't slow down the master problem too much, but so it does give some guidance to the master problem solution. Cuts should be strong and cheap. That is, they should be cheap to find, and they should be better than just saying no. Right? They should be better than just saying give me something different. They should actually, hopefully, cut off more than simply the one solution of the master. It should cut off a bunch of that solution space. Often it's the case that mix and interprogram is used for the master problem and constraint programming for the subproblem. There's no reason to do that, but often we can design these problems so that the master problem is solved very quickly with MIP, and the subproblems, as in this example here, are solved very strongly with the subproblem. We can do a tighter relaxation, right? So I mentioned that relaxations are important. So this was the relaxation I showed you. Each of these guys has a time window. And so what we can actually do is we can look at a subset of activities, look at the time that these two activities have to execute from whatever one of these guys is earlier to whatever one of these guys is later. And so the sum of these durations, the sum of these areas must be less than or equal to the sum of this area. And so what we can do is for a quadratic number of these subintervals corresponding to all pairs of earliest start time, latest finish time, we can look at a quadratic number of these subsets and enforce and add each of these constraints. Okay, it's going to look exactly the same as the earlier constraint. In fact, I think I have it here. So the single relaxation, this is what we saw before. This relaxation is going to look at all pairs, so all the jobs that have to execute between T1 and T2, and those are the ones where T1 is less than or equal to the release date, and T2 is greater than or equal to the due date. So we know that this job is fully within my interval, so all of its capacity is going to have to be used. And so that's what we call the interval relaxation. We can also do a stronger bender's cut, because these subproblems are actually pretty easy for CP. And so if a subproblem is infeasible, we can actually do something like this. We can heuristically remove an action, solve it again. If it's infeasible, we don't have to consider this removed activity in the cut. So we can, with some clever resolving of the subproblem, we can actually find a minimal cut, that is a cut such that any of the activities, if I remove it from the cut, I have a feasible solution, but it's still infeasible with all those activities in there. And so because the CP problem is actually so simple, even though it's still NP complete, I can solve this multiple times and generate much stronger cuts. So here's an example, 195 instances, 2 to 4 machines, and 10 to 38 activities. Logic-based benders, it solves to optimality 174 of the 195. It doesn't find even feasible solutions to 21 problem instances, and that's because it doesn't find a feasible, it doesn't find optimal, it doesn't find feasible. Okay? But you can see the total time here, the mean time is about 37 seconds. CP, okay, doesn't do very well, 6,000 seconds. MIP actually does better. Okay? On the other hand, both CP and MIP find feasible solutions to all the problems. So you can actually start to argue here about, right, who's best. MIP actually does pretty well, right? It finds and proves optimality with 167 versus 174, so it loses a bit there, but on the other hand, it actually has feasible solutions to all the problem instances. So there's an argument here that MIP is actually pretty good in this. All right. Questions? I have about 15 minutes left, given that we started 15 minutes late. Questions on the decomposition method? Yes?
Does LBDP has any other applications than job scheduling?
So this isn't job shop scheduling that I showed you, right? So this is a, job shop scheduling doesn't have that resource assignment.
Oh yeah, resource allocation.
So logic-based benders over the past, let's say 15 years, has been applied to a whole bunch of problems. So there's probably about easily 40 papers out there that apply to different scheduling problems. I've applied it to a location allocation problem. There's some computer process scheduling problems that's been applied to. So yes, it's a very general technique, general pattern of decomposition. So actually, if you think about what's going on, those of you who know what SAP modular theory is, right, what we're doing is the same pattern. It's delayed constraint generation, right? We have this global problem. We're doing a relaxation and not telling it about some of the constraints in the problem. And then we dynamically generate those constraints as we find solutions to the master problem. SAP modulo theory has a core solver, which is a SAP solver. In this case, it's a representational issue because there are some things that we want to solve with SAP that we can't easily represent in SAP. So linear constraints or other aspects of often verification problems. And what we do in SAP modulo theory is we have a core solver, which corresponds to the master problem, and we have what are called theory solvers, which correspond to the subproblems. And similar thing happens. It's a bit different in that the master problem is not solved to optimality, but we have a version of that in logic-based benders as well. But basically what happens is the master, the core solver, is doing some search and making some decisions in a SAP model. These decisions mean something to, let's say, the linear solver that's sitting outside and knows some things about the problem that the SAP solver doesn't know about. And when the linear solver sees a set of assignments that violate one of its constraints, for example, it creates a new clause and adds it back to the core solver. So we have this fundamental constraint generation pattern that you can see again and again in a number of approaches, SAP modulo theory being one of them, logic-based benders being another. And this is a very general approach to decomposition-based problem solving. Yeah?
And what's the optimality loss of decomposition model compared to the MIP?
So here, we're finding optimal solutions. So what we do, so because of the way we've set things up, okay, I'm not going to go back to my picture, but I'm finding the optimal solution to the relaxed problem. Okay? And then, if each of my subproblems is feasible, what I've actually done is I've found a solution that satisfies all my constraints. It was optimal, and it satisfies all my constraints, so it's optimal in my global problem. So this is an example of, because of the way we've modeled it, we are not giving up optimality. This is a complete solver. Okay? And the subproblems do not have to be feasibility problems. We can actually have optimization problems in there. It gets a bit more complicated, but that's something we can do as well. Any other questions? All right, so I think what I'm going to do is I'm going to talk about this problem, which conceptually is very similar. Okay, this is actually a real-world military aircraft maintenance scheduling problem that we can see exactly the same things that we just saw in this more abstract problem come to bear. So, we've got a repair shop, we've got a time window, a horizon, and we've got a flight program which has some plane requirements. So this is red and this is kind of cyan. That means it needs a red plane and a cyan plane. We're sitting here in the repair shop. As it happens, both the red plane and the cyan plane are good to go. So we can assign these two planes to this requirement. What happens now is there's a maintenance check. And with some probability, one of these guys might fail the maintenance check. But the flight program still runs, okay, with, at a lesser level of quality because it's got a subset of the originally required planes. After our flight program, we again do a maintenance check, and again there's some probability that afterwards it's going to fail the maintenance check. So originally, when this came to us, we were looking at this probabilistic model because we have this underlying model of the evolution of the resources of the aircraft. Okay, we have a sophisticated maintenance model that we can look at the probability that it's going to fail. And if it doesn't fail, how does that probability change after it's run the flight, after it's flown the flight? And then, if it doesn't fail again, how does that probability again change for the next flight? And so we have this sophisticated maintenance model underlying an awful lot of this that I'm really not going to talk about, because I'm going to talk about the optimization side of things. So, we actually have a bunch of flight programs, a bunch of missions to run. And what we need to do is we need to repair each of these guys and assign them to the flights. And of course I have multiple green planes. I have to decide which of the green planes I'm going to restore when. When should each craft be ready? When we came on this, somebody had done some previous work on a MIP model, which was terrible. And so we decided there's a logic-based Bender's model here. So we're sitting at time 0. We know the state of our machine, of our airplanes. Okay, in this case, these two guys are under repair. What if this flight requires these two planes? What happens is I've got a deadline, right? I have to figure out, is there a way that I can repair these two planes by that deadline in my repair shop? And for now, I'm going to think of a repair shop as just a single resource. In general, actually in our problem, there were multiple resources, so there was a more complicated scheduling problem underneath it. But the idea is I'm going to have some sort of resource requirement in terms of preparing that. So a set of people, some number of people, and there's going to be some processing time that those people are going to be employed, people and machines, in order to repair this plane. Similarly, this guy corresponds to some sort of job in my repair shop. If I get both of them done before the deadline, and this is what's required here, I'm good to go. So here's our approach. We know we're at time 0, we know the requirements here, we know the state of the machines, and we are representing a more sophisticated state of the machines. We're going to assign the aircraft to due dates, actually the start times, in order to maximize flight coverage. And flight coverage was this probabilistic measure of the likelihood that a plane was actually going to be available to fly the flight that's assigned. So we're going to do something like that. Given that, is there our schedule? So we're kind of doing things backwards. We're saying, if everything is okay, this is where I want to assign my planes. Now I'm saying, given that where I want to assign my planes, can I actually create a schedule that can meet the due dates that I've figured out? So this is my subproblem. Okay, in my repair shop, I need to come up with a schedule. If there is such a schedule, given that this maximized my flood coverage, I'm done. Okay, and what's going on here? A schedule. Well, these two guys need to be scheduled before that deadline. These two guys need to be scheduled for that deadline, and this guy needs to be scheduled before that deadline. If I can do that, I'm good to go. And so if there is such a schedule, I've got an optimal solution, because this was the optimal due date assignment, and I've now satisfied those due dates. If there is no such schedule, then I need to add a cut back to my master problem, so that it comes up with a different set of due dates for these plans. All right, so Xij is 1 if due date I is assigned to job J. And so this is an important point. I'm not doing a time index formulation. I don't care that this start time is actually 10 after 10 on Monday morning. Basically, I've got a small number of flight programs, 10 or 12 or 15, and I've got a due date that corresponds to the start of each of these programs. So that means that I, the due date, spans the number of I's, okay, is the same as my number of flight programs. I need a relaxation to my master problem, right? Up here I want to assign due dates. So what's my relaxation going to be? If I just do it blindly, not taking into account the capacity at all of my repair shop, I'm likely to have to iterate many times. So I'm going to do the same relaxations that I showed you before. In this case, it's a bit simpler because I don't have to take all pairs of due dates, of start times and end times. I can actually look at the due dates. So the week relaxation is to take the last due date, okay, take this area and realize that the sum of the areas of these jobs has to be less than or equal to the sum of this area. Okay, and that's what that actually looks like in the model. I can do the same thing that I did before with the tighter relaxation. It actually looks a bit nicer here. What I need to be able to do here, okay, is say by this due date, I've got a subinterval. And in fact, each of these due dates represents subintervals. All I care at this point, okay, is that these planes get repaired before this due date. I could schedule this green guy right at the beginning if I wanted to. That's fine. And so that means that this interval, what I want to do in this interval is do the blue, or the cyan, the red, the green, and the purple by this interval. Okay? By this smaller interval, I want to do the cyan and the red, and by this longer interval, I want to be able to do them all. And so now, instead of having n squared, a quadratic number of these constraints, I just have order n of them, actually order due date of them, one for every due date. Okay, and believe it or not, that's what that looks like. All right, so the cut. So what happens if my subproblem is infeasible? So hopefully this is going to show up. So this is my J's, the set of planes. These are my due dates. I've got a 1 here that says that the red plane has to be done by due date 1. And this is infeasible. Okay, my subproblem is infeasible. I can't meet all these due dates. What I can do is realize, hopefully you can see that there's a green thing right here. Okay? So all of these guys represent a subset of my Xij variables. And what I need to do is if I'm going to create a feasible schedule, at least one of my planes has to have a later due date. Right? Something has got to give. I got to relax my master solution in some way. Which basically means you can look at it two ways. One thing it can mean is this upper triangle, at least one of those guys has to be equal to 1. Right? One of my planes has to be moved to a later due date. I can take the flip side of that and look at this inner triangle here and say the sum of each of these green guys has to be less than or equal to 4. Okay? Which means one of these guys is going to have to be equal to 1 because I've got 5 things to assign. So what I'm saying is over this subset of variables, okay, at least one of them is going to have to be assigned to 0. Actually, no, stronger than that. At most, 4 of them can be assigned 1. And in fact, that's what we can do for a given resource, for a given number of jobs that have been assigned. I can do exactly that in a more general fashion. The computation results are as follows. So this is a log-log plot. This is MIP on this, and logic-based vendors here. Below the line is a win for vendors. Vendors, we're using mixed integer programming in the master, and CP in the sub-problem. And this is the number of problems that are at least 10% below this line. This is the number of problems that are 10% or more above this line. So you can see that over 90% of the problems we're solving substantially faster with logic-based vendors, and we're getting some pretty impressive runs. Like if you look here, we've got MIP problems that are taking, and these are actually timing out, and we're solving them in less than a second to optimality with logic-based vendors. Okay. And again, this is an optimal solution. Because of the way we structure things, we are finding optimal solutions. Here's another look at things that gives you a bit more. This is the tighter relaxation, this is the looser relaxation. It doesn't give you a big difference here. Okay? We are able to solve 98% of our problem instances to optimality in either of these cases. MIP by itself actually doesn't do too badly. It's about 4 times slower on average. Interestingly, if I run a dispatch rule, I find, but of course cannot prove, optimality in about 10% of the cases. And CP is terrible. So this is the number of solutions, number of problems it finds and proves optimal. This is a bit of an unfair comparison to CP because I'm sure CP has actually found optimal solutions. I can't prove it. So I wouldn't be surprised if in fact CP has found 80% plus solutions optimal, but can't prove it. Okay? But in general, if we're trying to find and prove optimality, MIP is significantly better than CP here, but the vendors is again substantially better to do it this way. And what I'm looking at here is this is the amount of time spent in the master problem, this is the amount of time spent in the sub-problem. Generally, you kind of want to look for an even balance between the master problem and sub-problem. There's some technical things going on there. All right. Questions? Yes?
How do meta-heuristics stand in comparison to these techniques?
So my goal here was to find optimal solutions, okay? And so find and prove optimal solutions. And so the answer is they don't do that, right? Meta-heuristics, certainly in general, will not find and prove optimal solutions. So we have a number of examples, not in these problems, but where we've taken these decomposition techniques and looked at the evolution, the solution quality over time. So we have complete techniques that, if given enough time, will find optimal solutions. And we say, okay, let's run it against a meta-heuristic. So let's say, given 0.1 seconds, 1 second, 10 seconds, 100 seconds, let's compare the solution quality of a state-of-the-art meta-heuristic versus something like this. And it's not always the case, but we have some examples on some scheduling problems with sequence-dependent changeovers, where the state-of-the-art for finding heuristic solutions before was fairly sophisticated ant colony optimization, and we are actually now doing better with a logic-based vendors approach based on the meta-heuristic instances and based on their criteria. So we're finding better solutions in less time, better heuristic solutions in less time, and we haven't given up optimality. That is, if left for enough time, we will find it improve optimal. Now, I don't want to say something too strong about that. I think you can find, if you're interested in good solutions, meta-heuristics are certainly good for doing that. And so what I just told you is a particular case where we showed we can play the meta-heuristics game as well, but I wouldn't state too strongly that this is going to beat meta-heuristics. Other questions? Rico?
A sort of higher level question. So if we were to go back to or look at the overall message that you've given us, So you talked about planning via constraint reasoning or as constraint reasoning, scheduling in a similar way. What is, do you think, the next challenge in terms of putting the two together, doing goal-directed reasoning within the realm of scheduling, perhaps using things such as these kinds of decompositions that you're referring to? Could you say a few words about them?
So I was interested in Roman's talk this morning because he was talking about decompositions for multi-agent stuff, right? But typically what he was doing, especially in that global local, he didn't talk about coming back, right, and having some cuts from the local solvers that got shared with the master cut, right? So the issue here is, and this is, I believe, very fundamental, is we've got two very different styles of representing the problems. So if you think about MIP and CP, we've specified the problem by a set of constraints. And everything is about this set of constraints. And everything works, you know, for example, the cuts are new constraints that we add. So if we think about some sort of decomposition, and in fact I have a paper called Planning Modulo Theory, which proposes such a decomposition that is very much based on this logic-based Bender's delayed constraint model. What do we actually communicate back from a sub-problem into the master problem? Right? We've got this transition system. Somehow, if we have a problem with a transition system and we want to really follow this model, we need to relax that problem. Right? In the multi-agent case, it did relax the problem by the local-global split. But if I take a single-agent planning problem, I need to somehow figure out, well, what's the relaxation of this problem going to be? How do I change the transition system? And then, if I can formulate the decomposition, what is the thing that I give back to the master problem that somehow changes the transition system, so the equivalent of a cut to go back, so that we have all the guarantees that we'll still find optimality and blah, 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 blah. Right? So I think that was an example towards your question about bringing these two things together. But I think one of the main issues is this difference in representation. The transition system that's represented in state-based heuristic search, that's represented in planning, and the constraint-based representation that's represented in optimization tools. And I think trying to understand how we can merge and work these two things together, to me, is a big open question. And there are some. I mean, I showed you the CP techniques, there are MIP techniques for planning, but I think there is still a lot of work to be done to understand how we can take these two very different representations and start to exploit things from each of them to combine them in a hybrid fashion. Other questions?
Okay.
All right, let me try to wrap up. Okay, so hopefully if there's one thing you remember, CP wins or loses by inference. Okay, this is my hand waving thing. That's not goodbye, that's informality, okay? So, if we have some problems with interacting combinatorial structure, right, these are what global constraints represent, and we can focus on them to do this local consistency reasoning. And in many of these problems, it might be difficult to find a feasible solution. So CP is not good at optimization. One of the things that I showed you, those results about how good MIP was, MIP is based on this relaxation that is reasoning about cost. CP, because it has this very general language, literally anything can be a constraint, does not currently have a generic relaxation. And so actually proving a solution is optimal is actually much more difficult in CP than it is in MIP because we don't have this cost-based reasoning, well, not for free, but as a core component. So there's a lot of work in CP for trying to understand how we can do this cost-based reasoning, but in many cases the optimality proof, even though we may find an optimal solution right away, very quickly, we then have to do basically the whole tree search before we know that it's an optimal solution. Okay, CP is very good at quickly finding good solutions and typically bad at proving optimality of those solutions.
Can I just clarify something?
Yeah.
And the reason for that is because if you're not using linear constraints, you can't guarantee a convex.
Well, so
whatever you call it.
Well, it's more general than that. We do not have a general polynomial time relaxation for constraint programming, right? So in general, it's a non-convex problem that we're trying to solve.
Yeah.
Okay, essentially, the MIP to LP convexifies, right, the problem, in which we can now solve it in polynomial time.
But we can't really convexify probably.
Well, we could, and some of the solvers are trying to do that. So, you know, CP Optimizer often runs an LP in the background because it has tried to introduce linear relaxations of global constraints. And there's some work on linear relaxations of global constraints, but it's not at the level that MIP does. So MIP is really LP and cost-based reasoning. Doesn't do a really good job about what CP is good at, which is that inference. Okay? CP is not very good at the cost-based reasoning, but does a very good job about the combinatorial satisfiability type constraints. Something I didn't mention, but the only way we can optimize with CP is if we have a problem that has strong backpropagation from the cost function. What this means is if I find a feasible solution, let's say I'm minimizing, well, I place a new upper bound on my cost function. I want to find something better. If that new upper bound propagates back to my decision variables and removes some values from the domains of my decision variables, then I have a chance, right? Because every time I have a new upper bound, more and more of my domains are going to be pruned. If, when I place an upper bound on a cost function, nothing really propagates to my decision variables, I'm essentially going to have to search most of the tree in order to prove I have no better solutions. Okay, and so this notion of backpropagation and make span, it's a max. Max propagates very well. The sum of completion times, for example, does not propagate very well. And so if I simply replace job shop scheduling, place the max, the make span, with the sum of completion times, MIP is actually competitive and sometimes even better than CP simply by changing that cost function, which isn't very good news for CP. Despite that, scheduling is one of the most successful applications of CP. Decomposition-based CP hybrids. Again, given these weaknesses, we might be able to design problems where we extract most of the cost reasoning and focus our subproblem on stuff that CP is good at, focus the cost reasoning on something that MIP's good at. Okay, so trying to understand where these solvers work better or less well might drive us to these decompositions, and because we can do these decompositions sometimes without giving up our optimality, this is a new technique for, or not a new technique, this is a promising technique for solving some of these very hard optimization problems. And with that, I'll advertise my postdoc position again, and thank you.
Okay, well,